And yeah, we'll take it away whenever you're ready.
Okay, thank you very much for having me to this very nice day. I hope you're all doing well. And yeah, it was a really nice first talk by Dana, and I'm looking forward to Alan's talk. Today I'll talk about phase transitions and algorithms, and in particular a certain type of phase transition, a first order phase transition, and what that means for algorithms. So one question I'm quite interested in is, when are phase transitions barriers to efficient algorithms? And there's different results showing that they can be barriers to efficient algorithms, but I want to know, are they always a barrier to efficient algorithms? And in particular, does the type of phase transition play a role? And so I'll discuss a very particular type of phase transition today, and show that, in fact, it does not have to be a barrier to efficient algorithms. To give these algorithms, I want to show that you can use some classical tools from statistical physics to actually design new algorithms. And in the other direction, I want to argue that using this algorithmic perspective, searching for efficient sampling algorithms, you can actually understand phase transitions in the physics models better. Okay, and so the new work that I'll talk about will be based on two papers. One is a joint paper with Christian Borgs, Jennifer Chase, Tyler Helmuth, who's in the audience, and Prasad Tadali, that will appear at Stock this month. And then another, at the end, I'll get to something about random graphs, and this is joint work with Tyler Helmuth again and Matthew Jensen. And this will be posted on arXiv by the end of the week, I think. So brand new work. And I think Tyler and Matthew maybe both are listening, so they should definitely pipe up if I say something too incorrect. Good. So what will I tell you about? The models I'll be talking about will be the POTS model and the random cluster model. So I'll first define these models and explain what kind of behavior we're looking at there. And then I'll talk about a few different definitions of what a phase transition is. And getting a little more detailed, I'll tell you what is a first order phase transition and what sort of aspects of the model lead to a first order phase transition. And then I'll describe some classical tools from statistical physics that have been used to understand the phase transition in the POTS model on the integer lattice and the random cluster model on the integer lattice. And these are contour representations and Pirogov-Sinai theory. And this will build on what Dana mentioned in her talk. Piles arguments and cluster expansions are certainly a part of these tools. And finally, I'll finish by talking about how these tools can be turned into efficient algorithms, both on lattices and actually random graphs. And please do ask questions in the chat as I go along. I'll either see it or the organizers will point out it, but I'm very happy to stop and answer questions as I go along. Okay, so let's start with defining these models. So the POTS model, and Dana mentioned the POTS model at the end of her talk, it's a probability distribution on Q colorings of the vertices of a graph. And we want to pick a certain coloring of the vertices with probability proportional to e to the beta times the number of monochromatic edges induced by this coloring of sigma. And then, of course, we need to normalize this to make it a probability distribution. And so the normalizing constant, the sum over all colorings of e to the beta times number of monochromatic edges, this is the partition function. And now this parameter beta, this is the inverse temperature, 1 over the temperature. And if beta is non-negative, this is the ferromagnetic case. So we prefer to see the same colors across edges. And as beta gets larger, this interaction is stronger. And if beta is small, the interaction is weaker. And today I'll only talk about the ferromagnetic case. So I've already specialized to a special type of algorithm, a special type of phase transition, a ferromagnetic one. Okay, and so here I simulated on a little chunk of Z2. I think this is maybe the 4-color POTS model. And on the left, you see beta is small, so high temperature, weak interaction. And what you see is that locally, if you really look closely, locally things do prefer to have the same color. You see little bunches of blue, bunches of pink, bunches of white. But on a global scale, it's disordered. If I tell you, well, this vertex over here is blue, it tells you very little about the chance that a vertex far away is also blue. And this is the high temperature regime. On the right is low temperature, so this means beta large, so the interaction is very strong. And what you see is actually there's one dominant color. Pink is dominant here. And of course, by symmetry, if I simulated it again, I would have 1 in 4 chance of seeing blue dominant or brown dominant or white dominant. But a typical configuration here at low temperature has a dominant color. And there's little islands of other colors in this dominant pink island. And if I'm lucky, if you look very closely, maybe you see that in an island of some color, there's an island of another color. So I think I am lucky. And maybe in like the middle island of white, let's see if I can even get my pencil to work. No, maybe not. Oops. There are islands of other colors.
We can also see your cursor if that's helpful.
Oh, you can. Oh.
Or your arrow.
Oh, interesting. Yeah, for some reason I can't get the pencil to work, but we'll see. We'll see how that goes. Let's see. Maybe I can get the pencil to work. Okay, so this is the behavior we sort of expect to see, and clearly there's something dramatically different in these two pictures. So what is the phase transition? And I'll start by talking about the phase transition on the integer lattice, ZD, and here D should be at least 2. And the Potts model undergoes a phase, let's see, I guess you didn't see that update, did you? 1 second. I'm gonna. Okay, so let's see. Okay, good. So on ZD, the Potts model undergoes a phase transition as beta increases. And there's a bunch of different ways to define this. And one is to take a sequence of boxes that tend to infinity and put different boundary conditions on these boxes. And one way to describe the phase transition is to say for small beta, the influence of the boundary conditions diminishes as the volume grows. So imagine we put all pink vertices on the outside of the box, and then we asked, is the origin more likely to be pink than another color? So if beta is small in the limit, this is not true. In the limit, even if you put all pink boundary conditions, probably the origin is pink tends to 1 over Q. On the other hand, if beta is large, then the influence of the boundary conditions does persist, and the probability it's pink is bounded away from 1 over Q. So that's one way to describe a phase transition. Another way to describe a phase transition is something we can talk about the torus. And so let's see here. Good. And so if we have the torus, so no boundary conditions or periodic boundary conditions, for small beta on the torus, correlations decay exponentially fast. So if I tell you a vertex over here is pink, then if I look far away, this tells you very little about the probability this vertex is pink. And this is uniform in the volume. On the other hand, if beta is large, then on the torus, we have long-range order. So if I tell you the color of one vertex, that makes it more likely a vertex very far away gets that same color. Okay, so these are two different definitions of phase transition, one in terms of boundary conditions and one in terms of the torus. Now, how did statistical physicists maybe 30 years ago prove things about the Potts model phase transition? They actually looked at a more general model to get maybe the sharpest results, and that's the random cluster model. And here, right, so what is a random cluster model? I'll show you how it's a generalization of the Potts model in a second. But what it is, it's a probability distribution on subsets of edges of a graph. So we have some graph G with a vertex set V, edge set E, and we want to pick a subset of the edges A with probability proportional to the following. We have some exponential factor, e to the beta minus 1, to the number of edges in the subset. And then we have a factor q to the number of connected components. And this is the number of connected components formed by the vertex set with that set of edges. So for instance, if A is the empty set of edges, then it's q to the n, the number of vertices. Okay, and q actually can be any positive real number. It doesn't have to be an integer. When it's an integer, there will be a connection with the Potts model. But this is really a type of tilted edge percolation model. So if we set q to be 1, then the number of connected components doesn't matter. And really, we're just picking edges independently with a certain probability that depend on beta. So it's a tilted edge percolation model. Now here's the connection with the Potts model. So let's say q is an integer. I want to describe to you the Edwards-Sokal coupling of the random cluster model with the Potts model, and I'll show one direction. So I'll take a random cluster sample, so a subset of edges, if you see these blue edges of this graph, and I want to turn this into a Q coloring of the vertices that has the right distribution. Okay, and so what do? We first pick a set of edges according to the random cluster model and determine the connected components. So here's a connected component here, here's a connected component here, here's a connected component here, and of course the isolated vertices are connected components as well. Okay, so we've picked a set of edges and identified connected components. Now what we're going to do is for each connected component, including the isolated vertices, flip a coin independently with probably 1 over q and assign a color. And so here you see that the connected components all received a single color for their vertices, and the other vertices got a color. And the fact is that this is distributed according to the Potts model with the same q and the same beta. And so this is a generalization. So this leads me to yet another definition of a phase transition. And here, a phase transition, we can plot the limiting value of some statistic or observable against beta. Look at the expected, let's say the expected fraction of edges that are occupied in the random cluster model. Plot this as a function of beta. And a phase transition occurs if there's a non-analytic point of this function. So a discontinuity or a discontinuity in the derivative. And now I'll sort of sketch a little plot of what it means to have a first order or second order phase transition. So on the y-axis, you should imagine on ZD, or the limit of boxes on ZD, what is the expected fraction of edges that should be occupied in the random cluster model. And a first order phase transition maybe will increase, but then we'll have a discontinuity here. Whereas a second order phase transition, maybe we increase and then we increase, but there's a kink in this function, but not a discontinuity. So there's a discontinuity in the observable plotted against beta on the left, but just a discontinuity in the first derivative of this observable on the right. And so a first order phase transition you might call a discontinuous phase transition, and a second order phase transition you might call continuous. And what I want to get across in this talk is what are some tools that statistical physicists use to understand a first order phase transition, what that means for algorithms like Markov chains, and actually how we can exploit the fact of a first order phase transition to find efficient algorithms for various problems, even at the critical point in this case. Okay, so what I'll talk about is actually the large Q behavior of the random cluster model. And so probably you've heard that if Q equals 2, then the Potts model is the Ising model. And there's quite a lot known about the Ising model. In particular, the phase transition is second order in the Ising model. But I'm interested in Q larger. And so what I'll talk about is Q large as a function of D. This might, in terms of the behavior, this might not be too large. Maybe this means that Q is 4 if D is 2 or something. But in terms of the proofs that I'll describe, this means that Q is some large function of D. Okay, so here's one property that the random cluster model on ZD has for Q large. Let's say on the torus, so we don't have to worry about boundary conditions. So for all beta, no matter what beta is, typical configurations either have very few edges, say less than 10% of the possible edges, or greater than 90%. Okay, and the probability that you're in the middle is, say, exponentially small in the side length to the d-1. Okay, so this is what I'll mean by no middle ground, that no matter what beta is, small, large, at-critical, subcritical, supercritical, you're not going to see typically anything in the middle. You're either going to see a lot of edges or very few. And also, if you condition on the number of edges, say you condition on the first event that there's at most 10% of edges or at least 90% of edges, then actually the model has very nice probabilistic properties, including exponential decay of correlations. So what I mean by that is if I tell you that this edge over here is occupied, is part of the random set A, and you look at an edge far away, the correlation between these two indicator random variables decays exponentially in their distance. So not only do you only see few edges or many edges, but if you condition on these events, you get very nice properties.
Well, there's just a quick question in the chat. Which observable is used to define the first or second order phase transition?
So it can be lots of different things. The one I'll use, let's say, is the expected number of edges that appear in this random set A. So let's call them occupied edges. You could, and for different models, you could describe different things. You could, for the Potts model, you could say, what's the expected number of vertices of the dominant color, the most common color. And there, what you would see is 1 over Q, 1 over Q, 1 over Q, and then a jump to something strictly bigger than 1 over Q.
Thank you.
Thanks for your question. Okay, and so what I'll talk about is a sort of a technique for proving things in this large Q setting that comes from Pirogov-Sinai theory. This uses contour models and cluster expansions, and in particular, this paper of Lanait, Messiger, Miraco, Soleil, Ruiz, and Schlossman in 1991 established this behavior for the random cluster model. And that's what I'll sort of describe. And eventually I'll come to algorithms. And so what do I mean by algorithms? There's two natural computational problems associated to a model, like the Potts model, the random cluster model. We want to approximate the partition function, Z, to say 1 plus epsilon multiplicative factor. That's the approximate counting problem. And we also might want to output a random sample from the model, say within epsilon total variation distance, and this is the approximate sampling problem. And the connection to phase transitions is as follows. So there's several very useful approaches to approximate counting and sampling, including Markov chains, the correlation decay method of White's, Barvanak's polynomial interpolation method. But all of these actually either are limited by or must somehow bypass a phase transition. And so the properties that we use for Markov chains to work for efficient algorithms is a fast mixing, but a phase transition can induce slow mixing. Correlation decay, we rely on some correlation decay property on something called a computational tree, but phase transitions induce long-range correlations. And Barvanak's method relies on having a zero-free region of the partition function in the complex plane, but a phase transition actually also you must have an accumulation of zeros on the real axis, moving towards the real axis as volume grows. So actually, phase transitions are barriers to all of these methods, and we must find some way to get around this. Okay, so for example, the Potts model. there's several useful Markov chains, the Glauber dynamics. And so to run the Glauber dynamics, you pick a random vertex in your graph and update its color based on the colors of its neighbor. The Swenson-Wang dynamics, this is more sophisticated, and this uses the coupling with the random cluster model. What you do is you pick a cluster and then flip the color with probably 1/q. And so in particular, above the phase transition point, at low temperature, when you have these dominant regions of colors, this actually is very effective because you can take that pink region and all of a sudden flip it to blue. And so the same bottleneck you would see with the Glauber dynamics doesn't apply for Swenson-Wang. So one thing you can show just based on this picture I sort of described is the Glauber dynamics mix slowly for beta, at least beta critical. And what's the bottleneck? So Dana talked about bottlenecks showing slow mixing of Markov chains. The bottleneck is something between mostly red configuration and mostly green configuration. It takes exponential time in the Potts model with Glauber dynamics to move from mostly red to mostly green when you're above the critical point. On the other hand, Swenson-Wang algorithm, the idea is to get around that bottleneck in particular, because we can move from mostly red to mostly green with just one move. Okay, so, but Swenson-Wang actually mixes slowly in many different settings at the critical point. And so here, this no middle ground that I said, this is the bottleneck. So going in the random cluster setting from very few occupied edges to very many occupied edges. And this has been shown in many, many settings. So Gore and Jerem for the complete graph, Borg, Chase, Fries, Kim, Tedely, Vigoda, Vu for ZD, and more refined estimates actually showing really the right dependence in the exponent by Borg, Chase, and Tedely. So not coincidentally, there are 3 of the co-authors on the first paper. So what they did for slow mixing, actually, we then adapted for algorithms. And I'll try to describe that as we go along. And then for random graphs that I'll mention at the end, Galanis, Stefankovic, Vigoda, and Yang showed that the Swenson-Wang dynamics mix at the critical point. And the slow mixing of Swenson-Wang really is a consequence of this first order phase transition where we have this no middle ground. And the middle ground is exponentially unlikely. And so this actually is the bottleneck that shows slow mixing. Okay, so please do ask questions if you have any. Very good. Okay, so I'll start to talk about how they prove these things in this classical approach. And the starting point is to say that the random cluster model, the Potts model has these Q ground states, these most likely configurations, all pink, all blue, all white, all brown. On the other hand, the random cluster model has 2 potential ground states. The disordered state, which will just be the empty set of edges. Okay, this maximizes this Q to the number of connected components factor, or the ordered state, and that's all edges. And this maximizes this factor e to the beta -1 to the number of edges. And so depending on what beta is, one of these might be the most likely configuration. Okay, and these of course correspond to 2 different things in the Potts model via this coupling. The disordered state corresponds to choosing the color of every vertex independently, or choosing the same color for every single vertex. Okay, so those are the 2 extremes. And then contours, and I'll draw some contours in a second. Contours provide a geometric way of taking a random cluster configuration on, say, the lattice, and separating them into regions that are ordered or disordered. Okay, and we'll see some pictures in a second. And the idea of Pirogov-Sinai theory is to use these contours and develop something called contour models to actually separate configurations into 2 classes, mostly ordered or mostly disordered. And there'll be some middle ground class that we'll show is unlikely as well. And what this leads to is 2 new partition functions. So Z disordered and Z ordered. The first making up, corresponding to these mostly disordered configurations, and the second mostly ordered. And these can be controlled via the cluster expansion. So Dana mentioned that, and I'll mention it as well. But there's some nice way to control this. And the hint that you can control this is in the statement I said previously, which was if you condition on having very few edges or very many, you have all these nice probabilistic properties. So by separating things, there is some hope that we don't have these barriers. Okay, so I'm going to give a rough picture of why you get this first order phase transition. So in these contour models, you're able to define some other partition function. I put a tilde because you actually truncate something, but let's gloss over that. And you can define, let's say on the torus, these limiting free energies f_dis and f_ord, which somehow control the asymptotic growth rate of this disordered and ordered truncated partition function. And in particular, by proving that there's no middle ground, it actually follows that the free energy of the model, so the real random cluster model on the torus, equals the maximum of these two functions. So there's a competition, depending on beta, between which grows faster exponentially, the mostly disordered or mostly ordered configurations. And on an exponential scale, whichever is maximum wins and determines the growth rate of the full partition function. And so in particular, we can actually define the critical beta as the point at which these two functions equal each other. Okay, of course, you have to show that there's only one point at which they equal each other, and so on. So I see a question in the chat. Now I'm able to read the chat myself. So is this true for all real or complex values too? That's a very good question. So you can certainly define these things in terms of complex parameters, and some of this will be true. In fact, a lot of it will be true. And one thing that you'll get out of this is that, say, some partition functions are zero free in some region around the real axis. You have to be a bit careful because really the parameter you're looking at is like e to the beta -1 instead of beta. But the answer is basically yes, that this is also true for complex values. Okay, so let's do a picture here. And so what I want to plot first is, let's say, f_dis. And so I'm going to plot that as a function of beta. And it's some nice function, nice analytic function. You don't see any strange behavior at the critical value for f_dis. But then I want to plot, let's say, f_ord. And f_ord, hopefully I can hit it right, is also going to be some nice function that grows. Okay, and they're both increasing, but they cross once. And where they cross, if I had drawn it a little bit better, would have been beta critical. And so what do you see for the free energy of the real model? You see that it looks like that, and there's a kink. And so for the free energy, you see this kink, so discontinuity in the first derivative of the free energy. Now this observable that I mentioned, which was the expected fraction of occupied edges, this is actually the first derivative in beta of f. And so you see how a discontinuity in the first derivative of this green function I plotted here leads to this jump in the observable. And so, this competition between these two states and the fact that there can never be any middle ground is what actually leads exactly to this first order phase transition. Okay, so hopefully if there's any picture you remember, maybe it's this picture. Good. Okay, and so what about at criticality? What can we say at critical? So at critical, z_dis and z_ord matched on an exponential scale. That's sort of by definition. But we can actually say a bit more. So in particular on the torus, let's say, if you look at z_ord of beta critical, this is q times z_dis, up to some lower order corrections. You can actually get smaller order corrections in n, in the volume of the torus or the side length. And this is what's called finite size scaling or finite size effects. But in general, z_ord is q times z_dis. And so let's see, there's a question. So in terms of the free energy, this is a second order phase transition. even though for edges it is a first order phase transition. Actually, yeah, so maybe I should have started with a free energy plot, because first order means there's a discontinuity of the first derivative. Okay, so this actually does refer to the free energy. First order discontinuity of the first derivative of the free energy. In a second order phase transition, the second derivative of the free energy would be discontinuous. So the reason it's the observable is discontinuous is because that's already the first derivative of the free energy. Good. So yeah, so we know basically the ratio z ord to z dis is q to 1. And what this no middle ground result tells us is actually that the partition function at critical equals z ord plus z dis plus something exponentially small, and say the volume to the d minus 1 over d. And what this is telling us is that at critical, what do you see typically? What you see is you flip a coin, and with probably 1 over q plus 1, you see something that's completely disordered, or disordered in the entire region. And with probably q over q plus 1, you see something that's ordered. You don't see configurations that say have a patch of ordered and a patch of disordered, or you don't see like macroscopic interfaces between ordered and disordered. This is what would happen in a second order phase transition. But in a first order phase transition, you see one or the other at critical. And in fact, we know in the case of ZD, we know like what the probability is that you see one of each. And so, as I said, this is quite bad if you're a Markov chain, this no middle ground. But this is quite good if you just want to sample from the model, because actually already you sort of know what you should do. You should flip a coin, and then you should just sample from this z dis or this z ord model. And we already said that these are quite nice. And so that really is the idea of the algorithms. Okay, so let me tell you what's new. What are the new results? And then I'll in the remaining time, I'll get to some of the more details. So the new result, and this started with a paper with Tyler Helmuth and Guus Rex, who I think maybe also is in the audience. The cluster expansion in pure Gauss-Hanai theory can actually be made algorithmic. And so when we write things in terms of contour models that I'll describe, we can actually turn the cluster expansion into an algorithm, an efficient algorithm. And the fact that this first order phase transition means that this actually is enough at criticality. You just have to approximate z dis and approximate z ord to get the approximation to the full partition function. And so the result with Borg, Chase, Helmuth, and Tedley was that we get efficient sampling and counting algorithms for the Potts model and random cluster model for large Q on, say, the integer torus at all temperatures, subcritical, supercritical, and critical. So there really is no barrier. This particular type of phase transition is no barrier to efficient algorithms. And then the very new work with Matthew and Tyler is that we can apply the same general approach to other graphs. And so in particular, graphs with enough expansion, like say random delta regular graphs, and we can get efficient algorithms for the Potts and random cluster model on random graphs at all temperatures. And again, this is for large Q as a function of delta. And then the final thing is that actually we were motivated to find these efficient algorithms, but actually we got quite a lot of interesting information about the phase transition on the random graph. And I'll have a slide later about exactly what we can prove, but we can find exactly the distribution of the weights of z dis and z ord at critical on the random graph. We can get local convergence, correlation decay, and all sorts of things. And so this is what I referred to, that sometimes this algorithmic perspective maybe can help us to prove something about phase transitions. Okay, so the outline for the rest of the talk, I want to give a very high level picture of what contour models are and mention the cluster expansion. I want to give at least a slide to say, how do you make these tools algorithmic? And then I want to, if I have time, explain what to do for random graphs, because random graphs, we lose some of the very nice geometry of the Euclidean lattice, Euclidean space in the integer lattice, but we gain expansion. And how can we make some of these notions work in that setting? Okay, so here's, I want to describe just how to construct contours. And so what I'm going to draw first is I'm going to draw a random cluster configuration. So hopefully this is going to work. These are the blue things will be occupied edges. Okay, so there's some occupied edges here. And let me say that the definition of these contours comes from this Borgs, Chase, Tedderly paper, whose main result was to prove slow mixing for Swenson Wang at criticality. Okay, so I have some set of occupied edges, these blue edges. And now what I want to do is actually imagine that my lattice is embedded in Euclidean space, and I'm going to draw some geometric objects that separate regions where edges are occupied from regions where edges are unoccupied. And the basic idea is that I want to take like a 1/4 neighborhood around occupied edges or around occupied cells, so full squares. And so for example, I have one edge here, my contour would just outline that. I have a square here, so my contour would outline that. Here I have like a square with an edge, so it goes around. Here I have some L and it goes around. And then here, this is a little bit more interesting object. I have to go around this outside. Oops, I shouldn't have these contours intersecting. Oh, maybe I slightly avoided that. And then I also have a contour on the inside. There. And so, you know, of course, there's a formal definition of what, how you construct contours, but at least for me, doing it once and doing the drawing made the most sense to understand these definitions. But what you see is that these contours are separating regions where the edges are blue, occupied, from where edges are not blue, unoccupied. And these contours, they cut through some of the edges, and that will be important. The number of edges that a contour cuts through will define as the size of the contours. Okay, so that's how you construct contours. And then what does this give you? Then you can really view a random cluster configuration geometrically. And so imagine you have a big random cluster configuration. I want the black in this picture represents the contours that I just drew. And then I'm coloring with blue any regions that are occupied. So the edges are occupied, and pink where they're unoccupied. And as you see, the contours can nest. Okay, so the boundaries between these regions are the contours, and contours, they don't intersect. They can nest. And actually contours, just the contour themselves, they can tell you which side is ordered and which side is disordered. By the way, I drew them in the first case. And so the way to say that is they have labels indicating which side of the contour is the ordered side and which side is the disordered side. And of course, you want the labels to match. So if a contour is inside another contour and it says out is ordered, then the other one should say in is ordered. But that's some way to construct a geometric picture of this random cluster configuration. And then what we want to do is separate these, the random cluster configurations on the torus into 3 different sets. And maybe I'll start with the last set. So if there's a contour that wraps around the torus, so that has winding number greater than 0, then we say this is part of the middle ground. Okay, so here I don't have any contours that wrap all the way around the torus. I just have small contours. But if we did have a contour that wrapped around the torus, we would say it's part of the middle set. If we don't have one of those contours, then we say, well, what's the dominant region that does wrap around the torus? If this is ordered, then it's an ordered configuration. And if this is disordered, it's a disordered configuration. So in particular, the big region here is blue, so this would correspond to an ordered configuration. And so that's how we split up these 3 classes of configurations on the torus. Okay, and so now I'll sort of describe how you can actually express the weights, the random cluster weights of configurations. And one thing you'll notice is if you had all blue, right, then your random cluster weight would be Q times e to the beta minus 1 times d to the number of vertices. That's just the number of edges in that region. On the other hand, if you were disordered, you would have Q to the number of vertices because you have connected, each one is its own connected component. And the point is that actually these contours, remember they cut across these edges, you get a penalty factor for these contours because you have some disordered edge, but its two endpoints aren't allowed, one of its endpoints is in some big connected component. So you're losing some degree of freedom. And so you get some exponential penalty in the size of the contour, the number of edges it crosses, e to the minus kappa times that size. Okay, so you can express the weight of a configuration in terms of this bulk volume factor out front times this penalty for the contour, and then you have to adjust the volume factor inside because you've switched from ordered to disordered, and that's the number of vertices in the interior of the contour. And so just a couple of remarks is that kappa, this kappa penalty factor is increasing in Q. And that's why these results hold when Q is large, because you can make this exponentially small to kill off some counting things. And beta critical is something like log Q over D. So when beta is around log Q over D, you see this exponential volume factor is close to 1. And so they balance. Okay, and so I'll just describe it really in pictures what's going on. One thing we can do is take this contour configuration on the left and just erase everything that happens inside and just concern ourselves with the outer contours. Okay, so that's fine. And now you can actually write a formula for the weight of all configurations that have this set of outer contours. And the point is you have a formula like you did before, but instead of just having this volume factor inside that it was all pink, you have to actually understand what possible contours could be inside that. And there's actually a good way to measure this, and that's z dis of the interior of gamma. Put disordered boundary conditions on this region that has some shape, and look at the partition function there. Okay, so we've sort of written this inductively in terms of some partition functions inside contours. Okay, and then that was just the weight of us for a fixed set of outer contours, but of course we can sum over all possible collections of outer contours. And this, Dana mentioned this, we're summing over some sort of collection of compatible objects. And here we're summing over these outer contours that don't overlap. So it's a compatibility condition, and this looks like some sort of generalized independent set model, hardcore model. Sum over compatible objects, product of some weights. Okay, and then there's some manipulations that they do in Pirogov-Sinai theory, and what you end up with is some nice expressions. So you end up with, let's say on the left, z ord of some region is some exponential factor in the volume times a sum over compatible contours. So now contours that just don't overlap, and product of some weight function. Now the weight function is a little bit tricky. So you can see on the right, the weight function is, it's e to minus kappa size of gamma, so that exponential penalty, but then you have a ratio of two partition functions. That's somehow the thing you need to control if you're going to show that this approach works. Okay, so and the theorem that they proved via Pirogov-Sinai theory is that for Q large, either K ord of gamma or K dis of gamma is exponentially small in the size. And so the first is true if beta is at least beta critical, and the second is true if beta is at most beta critical. In particular, these regions overlap. And so we can control things one way or the other. Okay, and what do you do once you have this? So you want to analyze things via the cluster expansion. And the cluster expansion works when you have some probability measure on collections of geometric objects, which are dilute, meaning the probability that they appear is rather small. And here we're going to use the fact that these weights are exponentially small. That's the parameter. And like I said, this corresponds to some very general hardcore model, weighted independent set model, where you have some weights. In this case, it was like this penalty times ratio of partition functions. and overlap is the neighboring relation. Okay, and so you have, Z ord or Z dis is of this form, sum over collections of compatible objects, product of weights. And then the cluster expansion, and Dana had this in her slides as well, it's an infinite power series for the log partition function. It's a sum over connected collections of contours, some combinatorial factor, and times product of weights. And this converges under some conditions, and the conditions essentially say that the weights are decay exponentially fast enough in the size. And that's what we verify. Okay, so that's very, very high level. I recommend reading elsewhere about cluster expansion and pure Gaussian theory. But I did promise to explain, at least briefly, why this can be made algorithmic. And the idea is that to get a good approximation to the partition function, you need to truncate the convergent cluster expansion, basically at terms of size log n. And so then we need to enumerate contours of size at most log n. And this is essentially like enumerating connected subgraphs in a bounded degree graph. And that can be done in polynomial time. It's like time n to the log delta. The trickier thing is computing these contour weights. K dis of gamma and K ord of gamma, because remember this involved ratios of partition functions. Okay, and we don't want to actually compute the partition functions because that would take too much time. So what we have to do is actually cluster expand these two partition functions. And so the whole thing can be done inductively. We start with the smallest contours where we can explicitly compute the weights, and then we build up by using the cluster expansion to approximate the weights K dis and K ord. And then sampling is done via self-reducibility, but on the level of polymers. Okay, so I guess 5 minutes left. Is that a reasonable?
I think we started a little bit late, so you're welcome to take a little bit more than that if you would like.
Okay.
I think we started about 9 past.
Okay, I'll see how it goes. So the last thing I want to talk about, so that was all for ZD and for the torus, where we have this very nice geometric description of contours. And really there's interior, exterior. You can use all the topology of Euclidean space to define these notions of contours. And what we've Tyler and Matthew and I have been doing recently is trying to apply this same understanding of a first order phase transition to a very different setting, which is a random delta regular graph. And so here we lose some of the geometry of Euclidean space, but a random regular graph is a very good expander. And so we want to know, can we replace geometry with expansion? And so the theorems that we prove are the following. So for delta at least 5 and Q large enough as a function of delta, we can find efficient approximate counting and sampling algorithms for Potts and random cluster model at all temperatures. So subcritical, supercritical, and critical via a similar approach. And what type of probabilistic information can we get out of this construction? So again, because we have control via the cluster expansion of Z dis and Z ord, and here really you can define Z dis just to be the contribution to the partition function from edge sets that are at most 1/10, and Z ord to be contribution from edge sets at least 9/10 of the edges. So one thing we can determine is actually determine the distribution of the ratio of Z dis to Z ord at beta critical. Okay, so this is a random variable because your graph is random, and it has some nice distribution. And as Q gets large, it looks like 1 over Q, but we can actually determine the full distribution. Another thing we can prove is exponential decay of correlations everywhere but critical. So again, if you look at the correlation between the indicator random variable that this edge is here and this edge is here far away, this should be exponentially small in the distance. And finally, we can show that local convergence. So imagine you pick a random vertex in your random graph and look at the depth T neighborhood. What's the distribution that the random cluster model induces? This actually converges locally to the corresponding measure on the infinite delta regular tree. So with free or wired boundary conditions. So I see Julian asked another good question. Is it obvious that there's a phase transition in this setting? So first you have to ask what you mean by a phase transition, because there's expectations going on. Is it obvious? I don't know if it's obvious. So it's not so hard to prove that there is a phase transition just by some naive bounds using expansion, let's say that. But what's harder is to identify exactly where this occurs and show that there's only one. So let me mention so Alan Sly will talk next about random graphs or random factor graphs. And there is quite a lot of study of, say, the Potts model or the Ising model on random regular graphs. And so Galanis, Stefankovic, and Vagoda and Yang should be there as well, gave a picture of the phase diagram for the Potts model for all Q on random regular graphs. What's different there is that they can actually get explicit formula for beta critical, which we think should hold for the random cluster model, but we don't know how to show it. But their notion of phase coexistence was at critical. Each of these partition functions has at least inverse polynomial fraction of the mass, where here with this method, we can actually get the distribution. And then there's been some other results on two-spin models showing local weak convergence to the corresponding tree measure. I'll say that the techniques are very different. So a lot of these techniques previously were based on verifying predictions of the cavity method from statistical physics, either using the first and second moment method in sophisticated forms or doing some type of interpolation. And these results generally hold on the level of free energy, so on an exponential level, where here our technique is something different. It's saying with high probability over the random graph, some expansion conditions hold, some small set expansion conditions hold. And once we know that, we can say something about every vertex in the graph. So in particular, every pair of edges satisfies this exponential decay of correlation statement. Of course, the drawback of our approach is that you need Q to be quite large, something like delta to the delta, and you don't get as explicit formulas as you do from the cavity method. But it's interesting to compare these two different approaches. Okay, so what do you have? Random graphs are very good expanders, and they're locally tree-like, which explains the connection to the infinite delta regular tree. But how do you use expansion? So the nice thing is that we have this picture of contours that are all nested, and you don't have to do that for the random graph case. So the nice thing about expansion is that the size of the boundary, where we were getting this penalty in the lattice case, is actually proportional to the volume. So if the penalty is big enough, this actually overwhelms the volume correction. So in some sense, this is easier than the Pirogov-Sinai theory case, because you just have to define polymers, not nested contours. But you do lose the geometry, and so you have to somehow argue indirectly about this factor Q to the number of connected components. This is not quite so obvious, because this is really a non-local interaction. Okay, so maybe the last thing I'll show you is just a quick sketch of the polymers, how we define these defects. So you have a random graph, and locally maybe it looks like a tree. And if we're imagining we're in the disordered ground state, we're imagining that most edges are absent. And so what is a polymer going to be? A polymer is just going to be a connected subgraph of occupied edges. So maybe these red edges were a polymer. Okay, and you gain something by having those edges. You gain a factor e to the beta minus 1 for the occupied edges, but you lose some connected components. So there's a penalty q to the minus number of vertices, or 1 minus the number of vertices. And so that's the weight function. That's the penalty for having this polymer. And the point is that if you're an expander, then this thing can be exponentially small in the size, at least up to some certain size. So that's actually the easier case. The more tricky case is in the ordered setting. So here, remember, you're imagining that most of your edges are occupied. So you think you have one big giant connected component. And now what's tricky is that imagine you have some disordered edges, so some missing edges. So let's say these three V's. And so these are disconnected as graphs, but actually their union disconnects the graph, whereas any two of them would not. And so what you actually have to do, the polymer corresponding to this, you actually have to inductively build this up. It actually is going to encompass all of this, the subgraph that's disconnected. And so this is actually the trickiest part of this new work, is coming up with the right definition of polymers in the ordered setting, and so that we can control the connected components. Okay, so that's all I'll say. Look on arXiv in the next couple of days for the paper if you want to read more. So let me give a summary. So the first order phase transition in the Potts and random cluster model, it's a barrier to Markov chains, even like Swenson-Wang. But it facilitates a very different type of algorithm based on sampling from ordered or disordered separately. And this allows us to find efficient algorithms at all temperatures, including critical, and we can follow the same framework in a very different setting for random graphs and obtain new probabilistic results. Okay, so maybe I'll skip over the open questions. You can read them as people ask questions, but thank you very much.
Thank you very much, Will, for a beautiful talk. So we've got one request for a question, so I'm just going to unmute Goose. Go ahead, you should be able to, oh, no, that's not working. Can you, yes, there you go. Feel free to ask your question.
Hi, Will, thanks very much for a nice talk.
Thanks for listening.
I was curious, can you say anything about the dependency on Q? Because from the cluster expansion, you get like, you say like delta to the delta dependency. Is there any way to improve this?
So that's a good question. I mean, these things should really hold. The behavior holds for Q quite small. So actually for say the random graph, it should hold as soon as Q is strictly bigger than 2. Mm-hmm. But I don't think, this method, this cluster expansion method is inherently perturbative. And so you really need some parameter to be large. What's nice about the random cluster model is Q can be large and you can get sharp results in beta. But I don't think this particular approach will work, be very sharp. And so, maybe the first question is, are there Markov chain algorithms that work? This would be a much better approach. And so my suggestion would be you would want to start the Glauber dynamics for random cluster model, start it in 2 different starting places. Start it at the all disordered and start it at the all ordered. And the hope would be that actually you would mix within each separate piece. That type of algorithm could work in a sharper sense.
Thanks.
There's a question from Agalos. Let me see if I can unmute him. There we go.
Yes, can you hear me?
Yeah.
Yeah. So you defined your contours geometrically. In my paper with Panayotis, we have we can define contours, abstractly for any graph, and they are nested. They seem to have the properties you want. So perhaps that could be useful.
Yeah, actually, Tyler and I and Sarah Cannon were really looking at your paper closely. I think this is a great open question, which is how do you extend these contour models to more general classes of graphs? And I think the condition that you need is some like a bounded cycle basis, right? And what's very interesting is that Hoos and Barvanok have a paper with a completely different method that also requires a bounded cycle basis. So there's some really interesting connection there. But yeah, we've been reading your paper very closely and trying to make some algorithms out of it.
Thanks.
And then Julian has another question. Go ahead.
Hi there. So in your results, you said you personally, but the distribution of the 2 bits of the partition function, the ratio.
Yeah.
Sorry, so just first to understand what that means. So that's distribution in the randomness of the graph.
Exactly. Yes.
I see. And what does that look like?
So
That-
if you
that
take the
distribution.
logarithm of the ratio,
Mhm.
you get a sum over independent Poisson random variables, an infinite sum over independent Poisson random variables with weights in front, and the weights are exponentially decreasing. And this should probably not be a surprise to random graph people, because these Poisson random variables are the number of cycles of length 3, 4,
Right.
5.
Right.
And so
Yeah.
on. And so that's exactly the form of it.
Okay. Okay. And sorry, just one more question. And what is known? I guess this was partially for Q small. In the random graph setting, say, yeah.
Yeah, so this paper of Galanis, Stefankovic, Vergoda, and Yang, they proved just the Potts model, so not random cluster, and using first and second moment method, they find a critical threshold and show that above critical, the state with exponentially small error probability, you have ordered states, and below critical with exponentially small error, you have disordered states. And then at critical, what they show is that the contribution from Z dis and Z ord, as they define it, is at least like 1 over n to some power. So it's not exponentially small, but it's also not a constant.
Right. And I saw the question in the chat, and I'm interested as well. It's interesting that you have this delta at least 5 condition.
Oh yeah.
Can you say something?
It probably shouldn't be there, but we're just using some facts about expansion in the random graph. And what made the arguments a lot easier to say that small sets expand by a factor d over 2. And that actually just sets in for the random graph at 5. There's probably other more sophisticated ways to define the contours to get around that, but then the arguments would have become pretty nasty.
I see. Okay. Yeah, thanks.
Great. I can't see any more questions. So what I'm going to do is I'm going to stop recording, and I'm